Hey everybody, this video lesson is going to cover the introductory notes for Unit 2, the electrons and the periodic trends. The chapters in the book that are covered are Chapter 6 and Chapter 7 in the textbook. This introductory video lesson is going to cover about 15 slides, so buckle up. Here we go. Before we get into the study of electrons, we need to talk about something that seems to be unconnected to electrons but is very much connected to electrons. So we're going to spend the first part of this presentation talking about some light characteristics. Now, if you remember your background information from honors chemistry last year, or whenever you took honors chemistry, you remember that the falling of electrons from a high energy level to a lower energy level emits light. That light can be identified or characterized by three different variables: its wavelength, its frequency, and its speed. Wavelength of light is the distance between two peaks or two troughs of a wave. So for example, if the light is traveling in a wave like so, the wavelength is the distance between the top of the two peaks, or it should be equal to the same distance of the troughs. Now, frequency is the number of waves per second that pass a given point in space. So I'm going to zoom in to give myself more space, but imagine you're standing here and there's a wave of light coming at you. The frequency at which it hits you is how many peaks or how many troughs hit you per second. That is frequency. You are standing at a fixed point and the light is traveling at you. The frequency of the waves and how often they hit you per second. So we zoom back out here and we can pull our screen into view. Frequency is measured in units 1/seconds. Finally, speed of light is c, and it measures at 3.0 times 10 to the 8th meters per second, and that is the fastest that light can travel. It is the speed limit of light. Light can slow down, but in a vacuum it is traveling at that constant speed, but it slows down as it travels through air or solids or liquids. In fact, it does indeed change its speed. It's variable, but its speed in a vacuum is 3.0 times 10 to the 8th meters per second. Now, how do these variables all relate? Well, in this nice formula right here, speed of light is equal to frequency times wavelength. This picture on the right just shows a representation of what frequency really is. Each of these waves of light represent 1 second of time passing. And this particular wave hits 4 cycles per second. 1, 2, 3, 4 peaks. Now this one hits 8 cycles per second, so we would say its frequency is double because you have twice as many cycles per second. And finally, the one on the bottom is the fastest of all. But it's important to note that their wavelength decreases as their frequency increases. They're inverse of one another, because the speed is going to remain constant assuming it's in a vacuum, 3 times 10 to the 8th meters per second. So in summary, it's important to know that as frequency goes up, like in this case you're going from 4 cycles per second to 8 to 16, as frequency goes up, the wavelength, as it shows, gets smaller and smaller. Now this visual is one you've seen many times before. It represents the array of wavelengths of the electromagnetic spectrum. Starting on the very right hand side here, we have the longest wavelength, shortest frequency, and those are radio waves. Working your way towards the left, you get a little bit shorter wavelength, increase in frequency, and eventually you get to microwaves and then infrared. And then we reach the point at which the wavelength is small enough, and this number is between 400 and 700 nanometers. Now this number is in meters, but if you expand it out into nanometers, it's commonly known that the visible spectrum is between 400 and 700 nanometers. So I marked those measurements on the blue side for 400 and the red side for 700. And then of course, as you continue to move to the left, you're getting smaller wavelength or increased frequency until eventually you get to gamma rays, which have incredibly small wavelengths, but they come at you super fast. Up until this point, we've only been discussing light and the electromagnetic spectrum, and I'm about to tie it in with how the electron plays a role. Hopefully you remember Bohr's model of the atom, which represents these energy levels above the nucleus. Each energy level represents a distance away from the nucleus, like this picture you see above. Let's pretend there's an electron starting out at the first energy level. The electron is subjected to some energy, maybe some electricity or some heat, and it jumps to an energy level higher than its original energy level. Upon returning to its ground state, it emits a photon of light. The energy that this light gives off is proportional to how far the electron falls. And it's also important to note at this time that the energy is conserved, which means the energy that is absorbed by the electron is equal to the energy output that it gives off when it falls back down. No energy is lost or gained in this process. Now we just spent a couple slides ago talking about how the wavelength of a light tells you the color, but we actually can do a couple of calculations that allow us to take the energy released by a photon and calculate it into a wavelength of light. Now the first one that I'm going to show you, the first formula I'm going to show you is one that relates energy and frequency. This formula says energy of the photon is equal to h times v, or Planck's constant times the frequency. Planck's constant is equal to 6.626 times 10 to the negative 34th joules times seconds. Fortunately for you, this number is listed on your sheet of constants and equations on the back of your periodic table. This formula alone also doesn't really relate wavelength of light with energy. But there's another formula that we showed you a couple slides ago that you can use to solve for frequency and then substitute it into this one. Remember, speed of light is equal to wavelength times frequency, and if I take this formula and solve for frequency by dividing by wavelength on each side, I get V is equal to C over wavelength. And what I do then now is take frequency and substitute it into this formula, and I create a brand new formula, and I get E is equal to hc over wavelength. And this formula now relates energy of a photon to wavelength, or wavelength to energy of a photon. Now this formula that I just showed you is not actually on your list of formulas. The one on the left, E is equal to hv, is, and so is C is equal to wavelength times frequency, but you'll have to put these two together to create this one all on your own. But I don't think that's too hard for you, since this is AP Chemistry. If I rewrite the formula to solve for wavelength, its wavelength is equal to hc over E. Keep in mind that wavelength in this case is always going to be measured in meters, so you might get a very, very small number if you're working in the visible spectrum, or even smaller in the ultraviolet, gamma, and that side of the electromagnetic spectrum. You'll be looking at a number that's like times 10 to the negative 9th, times 10 to the negative 10th, something like that. But that's okay. So to summarize my picture that I just showed you, energy of an electron can be lost or gained in only integers of multiples of h times v, or Planck's constant, times frequency. The system can transfer energy only in whole number quanta, or packets, and so the energy seems to have behave like a particle, and that's the photon concept of light. And now on the bottom here I have the formula that we just derived. The energy of a photon is equal to h times v, and E of a photon is also equal to hc over wavelength, and that was the one that I just derived for you. And that formula right there is probably the most important one for you doing the homework and problems going forward. If you take the light given off by atoms, electrons jumping and falling and emitting that light, and you collect that light and pass it through a prism, what you're going to see is that instead of seeing an entire spectrum of color, you're going to see very, very discrete or specific lines of color show up on the other side of that prism. This is what is known as a line spectrum. Each line corresponds to a discrete wavelength of energy and can be traced back to basically the amount of energy levels of electrons jumping and falling. This particular hydrogen emission spectrum represents the lines that you see when you pass the light that hydrogen gives off through a prism or through a diffraction gradient of some sort that allows for you to plot the lines at a specific wavelength. What can be concluded is that each line represents a single electron changing different energy levels. As we know, hydrogen has only one electron, but there are 4 lines on the emission spectra. In fact, there might be more lines that we don't see because they fall outside the visible spectrum of light. Some might be in the ultraviolet or even the infrared. But it is concluded that each line does represent a single electron changing different energy levels. And what that means is that the electron's energy can then be quantized, or in other words, has distinct values and not a range of values. Like I mentioned before, you don't see a spectrum of light, rather individual lines, known as a line emission spectrum. Up steps a scientist named Niels Bohr. What Niels Bohr did is he connected the emission spectrum of hydrogen with the structure of the atom. The emission spectrum of different elements has been known for a long time. The emission spectrum of different elements can be used as a fingerprint to identify a particular element. If you don't know what it is, you can electrify a sample of it and see its emission spectrum and see and identify it and base it off of a set of known emission spectrum. But what Bohr did was actually take the wavelengths of light, the 4 lines that you saw in hydrogen's emission spectrum, and apply it to a mathematical relationship. Basically taking the wavelengths of light and determining the energy levels and the energy in which the electrons jumped and fell. So he essentially bridged the line emission spectrum of hydrogen and the structure of the hydrogen atom. Before Bohr, scientists believed that the atoms looked more like a planetary model with electrons zipping around a central nucleus, but classical mechanics would suggest that the electrons would eventually slow down and collapse into the nucleus, and Bohr's model helped explain why the electrons don't do that. He proposed that the electrons in the hydrogen atom move around the nucleus only in allowed circular orbits and would not necessarily collapse into the nucleus. He coined the term ground state, which he called the lowest possible energy level state, which is defined as n equals 1. And these discoveries, along with Einstein's idea about the photoelectric effect, brought about quantum mechanics, and other scientists were involved, which we'll meet here later. This is a picture of kind of what I was trying to show earlier with the energy levels and the electrons being able to jump and fall. This is what Bohr's model looked like. It essentially looked like a multi-story apartment complex where the electrons lived on different floors. Electrons could jump between floors, but they would never be found in between the floors. This is what we mean by the concept of quantized energy levels. The electrons exist here or here, but never in between. And when an electron jumps from a low level to a high level and then falls back down, it emits energy in the form of light, a photon, which can be then calculated into a wavelength and assigned a color. If the energy represents a wavelength outside the visible spectrum, then that would also be noted as well. The strengths of Bohr's model is that it correctly fits the quantized energy level concept for the hydrogen atom, postulates only certain allowed circular orbits for the electron. In addition, it describes the concept of how the electron is brought closer to the nucleus, energy is released from the system. But where it fell short is that it only works for hydrogen. The math just didn't work out for other elements. And the electrons don't necessarily move around the nucleus in circular orbits, because the world is not two-dimensional. The world is three-dimensional, and we need to account for that difference in our atomic model. So Bohr's model was quickly amended, and in steps the quantum mechanical model of the atom. The first help came from a physicist named Werner Heisenberg. Bohr suggested the electrons lived on these energy levels and traveled around in circles, but Heisenberg said, well, wait a minute, maybe it's more complex than that. The electron's movement is so fast and so variable that it's not really possible to precisely know both the position and momentum of a particle at the given time, which includes the third dimension. So essentially, the electron is unable to be tracked. We know its position, but not its momentum, or where it's going, or we know where it's going, but not where it's going to be in a split second from now. Because as soon as you look at an electron, you shed energy on that electron, and the electron changes position accordingly. Now, there was a period in time in AP chemistry where we actually calculated the uncertainty of an electron. That's not something that we need to do now. It's not something that we are tested on the AP test. Just know that Heisenberg's uncertainty principle helped amend Bohr's model to help explain the way electrons move more clearly. And the final person to step in and help was Erwin Schrödinger. He developed a wave function that allowed to explain the movement of electrons around these energy levels. The advantage of Schrödinger's equation is that it took into account the energy levels of every electron, including the nucleus, so it could be applied to all atoms, not just hydrogen. What it did, though, was add a level of complexity to what the electron cloud looks like around the nucleus. It's no longer a nice spherical shape. As you know, these electron orbitals take on many strange shapes, which we will outline in great detail in the next couple days. Now, a final word of note on Schrödinger. He's probably best known for his thought experiment using a cat in a box with some or some radioactive material, and that in fact has nothing to really do with quantum mechanics. It kind of does, but is beyond the scope of our class. But if you're interested, click on the link on the notes. There's a nice little video. It talks about the concept of superposition, which is not really something we're interested in talking about. I mean, I guess I'm interested in talking about it, but it's not something I can spend a ton of time on. So anyway, that's this video lesson. Thanks for listening.